guys, I will be discussing problem 10801 on UVA. It's a graph theory problem. So I'll just explain the problem statement real quick. So the problem statement says that we have a building. Building has around 100 floors uh, with zero based indexing. So the height of the building is constant. It's 100, and we have a bunch of elevators. So these elevators, the number of elevators uh, can be from 5 to 1, so they won't exceed 5. And what we are given is A, for each elevator we are given how much time it takes to move between one floor, so like Fi and Fi plus 1, how much time it takes to do that. And we are also given the set of all the floors that it can visit. Like the first elevator could be said to have a speed of, like, let's say 5 seconds per floor. So if it wants to move from the 0th floor to the first floor, it will take 5 seconds. And it can also be the case that it might not be, like, it cannot open at every single floor. So if there, suppose for this case, let's say the building has only like 6 levels, it might be that it can only open at level 2, level 0, and level 5. It can obviously pass through these levels to reach level 5 from level 2, but it can not open at level 4 or level 3. That means a person can get in at any of these levels and can only get out at any of these levels. Um, Another thing which is very non-intuitive, which is given in this question, is that suppose there are two elevators, like E1 and E2, right? And for example, yeah, initially, let's say we go from E1 to um, some floor, let's say the fifth floor, and suppose it takes us 100 seconds. And now we want to switch elevators. Now, of course, if we want to switch elevators, we must also, like, it should be able to open at the fifth floor. So we are considering that is given. And E2 is also opening at the fifth floor. So irrespective of wherever E2 is located in the building currently, it will always reach the fifth floor if called for in 60 seconds. Irrespective, even if it is like traveling at 1,000 second per floor speed, if no person is traveling on it, it will always reach whichever floor you want it to. If you are calling it, if you are switching from one elevator to another, so if you are calling it at the fifth level, if you are getting out of E1 and you are calling E2, you will have to wait 60 seconds. But only if you are switching elevators. There is no other constraint. Now, what do we have to find is, um, given all this information, we want to find what is the minimum time in which we can reach the kth level, zero based indexing, right? So, like, I'll give a small example. Um, Suppose there are only like 6 levels, 0, 1. Let's take 7 levels, and there are only let's say two elevators. There's a lift here, and there's another elevator here. Um, and this elevator is traveling at, let's say, the speed of 2 seconds per level, and this is at a speed of like 3 seconds per level. And you want to reach, let's say, the fifth floor. Now, what we are given is that this elevator even can only access, let's say, the third floor, the sixth floor, and the 0th floor as well. It has to access the 0th floor. You cannot enter. Initially, you are standing here. Initially, you are at the ground. This is also given. But you cannot enter elevator if it does not open at the ground level. And this elevator at the sixth and the fifth, it can open at these two levels. Right? Suppose this is the question. and it's traveling. It's 3 seconds. It's traveling at 3 seconds. Um, and you have to find the minimum time. Of course, there is only one way, I think, to reach the fifth floor using this, and that is you can go from the 0th floor. You can take this elevator up till the sixth floor. This will take you around 12 seconds. Then you have to get out of this elevator, and now you have to um, take you have to call this elevator, so it will take another 60 seconds. See, you don't have to think about like in 60 seconds it might not be able to reach. Like if this was higher and its speed was very slow, like 50-second per level, will not be able to reach the sixth level in 60 seconds. But the question says that it will always reach the level, any level you call it at, after getting off an elevator. If you call some other elevator, it will be there after exactly 60 seconds, not less, not more. So this is given. This time of traversal between levels depends on the speed, but this calling time on switching the elevators, this is like you can assume in 60 seconds it will reach there no matter how. And now from here you can go to the fifth level, because see, this elevator cannot access the fifth level, but this guy can. And this will take another 3 seconds. So the answer will be 12 plus 60. It will be 75 seconds. Um, when I was solving this problem, it took me quite a while. A few issues I was facing. One approach which came to my mind was something that maybe I could use dynamic programming. If This was the first approach which I thought of. If I'm at the um, ith level, and if I want to be able to exit at the ith level using the jth lift, then what would be the minimum time for that? Uh, but this didn't seem quite right, because I could not get a good recurrence, and it's also possible that we might have to go to a higher level first and then come down to a lower level by switching the lifts. Either it might save more time, or either because one of the lift, like in this case, we had to go up and then we had to go down. Sometimes might if we might only have to go up. We might not need to go above the fifth level. So this did not seem apt. It did not seem correct. Uh, Another method, like I read the problem was for Dijkstra's algorithm, so I tried to think for an approach for that, and this is what I came up with. Let's suppose initially, let's try to simplify the problem a bit. Suppose we have like even eight of these. Let's just take three left. This is good, and we have a building with some levels here. And let's ignore the switching time, like the 60-second time which I told before. Let's say that whenever you call an elevator, it will be there in 0 seconds. Let's just think of it that. For example, if I'll represent this using red. Let's use this. Let's use this. And suppose we need to reach this floor, right? And we are given a bunch of things. We are given like I'll be representing this in the form of a graph. So I'll be explaining what I'm trying to represent using the graph. Suppose it's given like this. And 250. Let's it's actually black. Okay, so what does this graph represent? It represents what all stations, like if I had to hop up, what all stations could I reach for the red lift? Like these all these stations, they're accessible for the red lift. I can get off at any of these. I think this is not clear. Let's Yeah. For the red lift, I can get off at any of these levels. Similarly, for the blue lifts, I can get off at any of these levels. Actually, all these graphs, they will be bidirectional because the lift can go up and down. So, and like for this black, the E3 elevator, I can go at this level and I can move back and forth between these levels. Uh, Now you might be asking why my graph edge is not like I'm not taking this edge. Like this edge will also this is also a valid edge, but for simplicity, I don't want to make lots and lots of edges. So this is as good as this. Uh, doesn't matter if we're taking these two edges or we're taking this one edge. I just don't want to add lots and lots of edges because then the number of edges will be of order n square, and I think this also works fine. Now just ignore for right now that there is any uh, time to change the elevators. Like there was a penalty, right? If we suppose there are two possible paths here. I think more than two, but I can say two right now. Let's suppose one of the path is that I go from here and then I move here, uh, then I go up here, then I go up here. This arrow actually does not mean I'm getting off here. Um, I just make a full edge. I think this is. Uh, so I'm going from here to this level, and then I can use this elevator to come back here if I want, and can then use this elevator to go up again. This is like one possible way of movement. Another possible way of movement could be like I could just take this elevator, I could just take this edge and then I could take this edge, like these two edges. That could also be a valid path. Now, if we are ignoring the time to switch between elevators, like if I get off at this floor and if I am going to some other elevator, I'm saying that that takes practically no time. If I get off at this floor, I don't have to wait for some elevator to come here in for 60 seconds, which was initially given the question. I'm saying that it comes in 0 seconds. So what we could do is we could treat all these edges to be of the same color because there is no distinction between them. We don't pay any penalty for using uh, a blue edge after a red edge or a black edge after a blue edge. We don't pay any penalty for that. So how would we solve the question then? If this was zero, how would we solve it then? I'll just make all the edges of red color. I don't remember exactly these were this. So that's like uh, this. Yeah, I think that was one more. It's like this, something like this. The yellow is the one where we have to get off finally. We have to find the minimum time to reach there, and we are starting here. So now since there is practically no penalty for switching the stations, we don't have to worry about that. So we can treat all of them to be the same color, and now we can simply run a Dijkstra algorithm. Uh, we can consider this as a weighted graph and the levels as nodes, and the what would be the weight of edge? It would be the time it takes to move from one level to another, taking that edge, and that would be equal to the speed of the elevator into the difference between the levels. So now we can just start a Dijkstra from the kth level, and after completing the Dijkstra, we'll just print out the minimum distance if it's reachable. It might also be the case we might never be able to reach the kth level. In that case, we have to print out impossible. But I think now it's a simple Dijkstra's question. So it's the question is like transformed to just the fact that we have a bunch of uh, nodes and we had some like bidirectional edges. Like all these edges are bidirectional. So, like suppose this is sort of a graph, and we have to um, find the minimum distance between these 2 points. These 2 points, we can just run a simple Dijkstra's uh, algorithm. This would suffice if there was no penalty for switching the elevators. But the problem here is that now there is a penalty, right? If we switch an elevator, we have to pay some cost in terms of time. So how do we represent that in a graph? So this was like the main learning point for this question. Now the idea is good. It's a good idea. I will also model the cost or the penalty which I have to pay while changing the elevators in the graph itself. So initially I was representing the graph as consisting of L levels. But now I will represent the graph consisting of L into number of elevators. For each level, I will also depict the number of elevators for this level. So in this case, since there were three uh, elevators, I would have three of these for each level. Now, when the like in the question, we are given like for each elevator what all levels it has access to. So like for elevator 1, this would be for our concern for creating the graph, creating the edges, adding the edges for elevator 1. Similarly for elevator 2, elevator 3, suppose like we are given something like this. I prefer adding the edges like it. Even if you add an edge like this, you can still, you know, use these two instead of this. Like there would be no extra penalty. Like I think that is kind of obvious. So I just made edges for alternating flows that I could access. Like if these are the flows, these 4 flows I can access. So I just made alternating 3 nodes for them, 3 edges for them. For similarly for E2, I'll make some other suppose this, and for E3 I'll also make some other. And now K is this level. Let's suppose this is the kth level, which has 3 elevators. So in my Dijkstra's algorithm, I have not covered one part, that how do I model the penalty incurring while changing the stations, but some of you might have gotten the hint. Um, but simply if I could just fix that part in the graph, I could run a Dijkstra by having these at my starting nodes and then calculating the minimum distances for all the other nodes, and then out of all these 3 nodes at the 0th level, I would find out which one has the minimum distance, because all these 3 nodes belong at the 0th level. This belongs at the kth level. I'll just print the minimum of these. Now, how do I show the penalties while changing the station? That is also simple. We can just have, see, I can change stations from this elevator to this elevator. Stations, elevators, whatever, they're the same thing right now. So like this change I can do, this change I can do, and this change I can do. These 3C2 changes I can do right now. Like these are all the changes I can do. I can move from this elevator to this elevator, this elevator to this. All of these has a cost of 60. So like I'm just making a bigger weighted graph and I'm adding these distances. I'm adding these edges with weight 60, and the rest of the edges were like it was before, like we constructed for this graph. The difference in level in the speed, these edges will have separate weights. Now you can just run a simple extra. So this was the key point on how you should be um, converting your graph, or maybe have more dimensions in the graph. I would say like it has only one dimension right now, or it has two dimensions, uh, to incur some special penalties. So that's all for this video. If you want the code, I can send the pavement link. Thank you for watching. Bye.